How does the mathematics behind the theory of general relativity relate to contact mechanics? That's a question that I'll get into in today's talk. I'm Brian Giffen. I'm an assistant professor at Oklahoma State University. And recently I had the privilege of presenting at the International Conference on Computational Contact Mechanics. It's a lot of C's. But today I'll be presenting the work that I presented there on this new approach that I've been developing for the development of contact discretization methods, specifically more focused on volume-based discretizations for contact. So to give you a little bit of context on what exactly do I mean by volume-based discretizations for contact, it's worth giving you a little bit of background on the different approaches that people have pursued in this domain. So just to provide even a little bit more context, typical approaches for solving problems numerically that involve contacting bodies involve usually computing differences in the position of points on two potential interfaces that might come into contact by usually figuring out which 2 points might come into contact on two different surfaces by doing usually geometric projections of points from one surface onto another, and then computing all the necessary quantities of interest over each of those two different discretized surfaces, ignoring that there's some intermediate space in between those two surfaces. In contrast, some alternative approaches, which I'll broadly term volume-based approaches for the discretization and enforcement of contact, actually considered that the gap or the void in between those two surfaces can be used for the purpose of enforcing and detecting contact. And it has several potential advantages, but broadly speaking, it still suffers from a few different limitations. And it kind of comes down to the way that the contact constraints are formulated and represented in this discretized setting. So some of the history of this method, comes all the way back to the work of Oliver and in the development of the so-called contact domain method, which involves discretizing the interface between two different surfaces in potential contact using a collection of conforming finite elements. And this was an interesting idea that supposed that you could define a gap function that measures the apparent separation between points on different surfaces, not in terms of just discrete values of that gap function, measuring the distance between those two surfaces only, but instead, this contact domain method supposed that the gap function could be defined in a continuous fashion over the entire intermediate domain. And in doing so, you could then, pose integrals over this intermediate domain to evaluate contact Mortar integrals or penalty-based enforcement strategies, and apply conventional finite element technology to do so. However, it was still restricted in the sense that you could only really work with a single layer of these contact domain elements, and you had to choose a particular base side from which these gap functions would always be measured or evaluated. So it was a little bit constrained in that way, but it nonetheless got people thinking, what about these alternative approaches? What if we did choose to discretize this intermediate domain using conforming finite elements and do our contact enforcement there? It's not so different from some of the original conceptions of contact gap elements, which effectively treated the enforcement of contact as being, between two matching nodes or two matching surfaces that had conforming geometry on both sides of the interface. Kind of a notable extension of that same concept came about through the so-called contact layer elements. These were effectively like a contact gap element, but had a little bit more flexibility in terms of how you defined the gap between the two surfaces in contact. It's essentially like you had these thick shell elements that had a similar kind of in-plane description of the gap between two surfaces defined in this parametric representation. And here too, it's supposed that you could have a kind of an almost continuous definition of a gap function going from one surface to another. But again, it still suffered from some limitations. You had to have conforming, or matching surfaces on both sides of the interface in order to insert these, contact layer elements. So you had some constraints on the geometry, and you could only have a single layer of these. There were some other limitations with respect to the idealization of their kinematics, but anyways, I won't go into that. Other types of approaches that are going to be somewhat similar to what I'll present in today's talk include level set methods. And these were actually originally conceived in the context of particle methods, mesh-free particle methods, where it's not so clear how exactly you would even enforce contact between two different point clouds, where there is no description of the boundaries of those two bodies represented in terms of these mesh-free particles, let alone where those two surfaces would come into contact. And so the approach suggested by Chi et al. Out of J.S. Chen's group was to choose to define this level set function, whose value was equal to minus c on one of the bodies and plus c on the other body. And the level set of this auxiliary function would give you a description of some contacting interface between those two bodies. And that was kind of a cool, novel concept, but it also broke down in the case where that level set, had, a gradient that was, not well defined, let's say. So if those two surfaces were to really, or those two bodies were to, interpenetrate sufficiently, now it's not so clear what you would do if, let's say, the gradient of that level set function is no longer, a finite value. So in that circumstance, it didn't really make a whole lot of sense to work with that. And it didn't really extend to other domains where you might want to apply the same concept, let's say for, again, a volume-based discretization of contact between two distinct surfaces, where you do actually know what those surfaces look like ahead of time, not necessarily thinking in terms of mesh-free methods. And then the last example that maybe exemplifies this whole area of volume-based contact discretization methods is the third medium approach. And this is, originally proposed by Wriggers, but it's since gained some following and has, developed in other areas. They've included frictional contact. People have demonstrated it's really nice for solving problems, especially for optimization and topology optimization. It's kind of a nice alternative way and a smooth way of treating contact. The way that it works is that in general, you would consider two bodies in contact, and you can discretize that intermediate domain using conforming finite elements, but you're not restricted in terms of the number of elements you would have through the thickness of this intermediate domain. Nonetheless, the thing that you have to do with this third medium approach is you have to assign a fictitious material to this intermediate domain, such that it has a finite stiffness, but it's relatively soft compared to the stiffness of the two bodies that are in potential contact. As the two surfaces come closer and closer together, and this intermediate volume collapses, you would like for that material to stiffen up, almost like it undergoes some kind of consolidation effect, and such that it disallows interpenetration from occurring. But of course, that precludes the possibility that you would ever have those two surfaces perfectly touching. So you're always sort of regularizing the contact problem. You're never exactly enforcing that the gap between those two surfaces is directly equal to zero. So it's always an approximation, but it has some other nice benefits, as I said. It smooths out the transition from no contact to in contact, and that has some beneficial properties for the numerical solution and enforcement of contact, besides also, regularizing the contact enforcement, which has some benefits in computing gradients in the case of like an optimization problem or an inverse problem involving contact. Nonetheless, we'd like to do better. We'd like to see if there's a better way to do some of these volume-based approaches for contact, and that's precisely where the proposed methodology fits into the picture. So, building on the same kinds of concepts of supposing that we can fill in the void between these two surfaces and start trying to enforce contact on that intermediate domain, using it for the description of and enforcement of contact constraints. So the starting point for this whole new method is very similar in nature to some of what I presented on the last slide. Suppose you have two bodies in potential contact, and you have two surfaces on each of those two bodies, gamma 0 and gamma 1. And in between those two surfaces, I have some intermediate domain, sigma bar. It's some two-dimensional domain in this example, but rather than treating it truly as a volume or a two-dimensional volume in this example, suppose instead that that was a hyperdimensional surface. So rather than considering points within this intermediate domain as having coordinates x, I also equip those coordinates with some auxiliary coordinate, which I'll call alpha, where alpha ranges from a value of 0 on gamma 0 to a value of 1 on gamma 1. And it smoothly and continuously varies in between. So if you were to view this in kind of a three-dimensional plot with this auxiliary coordinate alpha on this vertical axis, you would see that this domain certainly has coordinates x, but it's also equipped with this auxiliary coordinate alpha. All right, so what's the point of introducing this alpha, and what exactly is its interpretation in this context? Well, alpha in some ways can be thought of sort of like a level set function. Suppose I were to consider a particular slice through this hypersurface measured at a discrete and constant value or elevation of alpha. So pass a plane at a fixed height of alpha through this hypersurface and can find what's the intersection of that plane with this hypersurface or hyper dimensional interface between these two surfaces of interest. I would get another intermediate curve that is effectively the level set of alpha, if alpha were to be defined with respect to the spatial coordinates x. All right, so given that, I can certainly determine different geometric quantities of interest, things like what's the normal to this level surface, which is really nothing more than the normalized gradient of the level set function, alpha in this case. But also I can define another related geometric quantity, which I'll call g. And g has sort of an interpretation that's analogous to the gap function in classical contact mechanics contexts. But this gap function also, effectively characterizes the hyperdimensional component of the hypersurface normal vector. It's effectively the vector that is strictly perpendicular to this hypersurface of interest, which has a component in the plane of the original spatial domain that's aligned with the normal vector n to a given level curve, but otherwise its hyperdimensional component is equal to minus g. And we'll see exactly how we define this extra quantity g. It turns out you can define both the normal and g not in terms of the gradients of alpha, but instead in terms of some other quantities, which we'll get into momentarily. Okay, so now the next step, rather than really considering just one of these intermediate curves, gamma sub alpha, for the purpose of posing Morter integrals or doing any kind of integration over this intermediate surface, suppose instead that I were to consider all of them taken together as a parameterized family of curves. And if I were to do this, I would define what is essentially a foliation of this intermediate volume, this sigma bar. And the nice thing about doing this is that according to the co-area formula, you can actually convert a volume integral posed over sigma bar, this intermediate volume, into an equivalent foliated integral, or an integral that is parameterized by alpha over the entire foliation of sigma bar. In other words, an iterated integral over the full parameterized family of intermediate curves, gamma sub alpha, ranging from alpha equals 0 all the way to alpha equals 1. So it's kind of like I say, I can either integrate over this volume or I can integrate over the slices of that volume. And I'm doing basically the same thing. That's the nice thing about this co-area formula. And it's also nice because in general, supposing I wanted to integrate over this intermediate volume, that makes sense up to the point when that volume becomes degenerate, when those two surfaces are perfectly touching each other. The volume form, dv, becomes null, and you can't really evaluate this integral in a meaningful way. However, if you multiply dv by the norm of the gradient of alpha, then that particular quantity actually remains well defined even in the limit as those two surfaces come into contact, or even if they were to invert. So whether that volume becomes null or negative, it doesn't really matter. If I'm evaluating integrals in this iterated sense over the foliation of that domain, then that remains perfectly valid, even if I have a null or negative volume. So it will turn out to be the case that it's actually more appropriate to carry out any kind of integration over this intermediate domain as an equivalent iterated integral over the foliation of the intermediate domain. Okay. Now, the other piece of the puzzle that we have to supplement all of this interesting, developments with is something called the delta-delta alpha derivative. This concept was originally introduced by Hadamard way back when he was studying the calculus of moving surfaces, a concept that's been more recently formalized by Grinfeld, and you can find some references and even a textbook that goes into a lot of the background online. But effectively, this delta-delta alpha derivative, it's a quantity that is like almost like a material derivative in some respects, but it has a nice geometric interpretation. Suppose I have 2 points defined on adjacent curves, gamma alpha and gamma alpha plus delta alpha, separated by just a tiny little difference in alpha. Now I could pick off 2 different points that are effectively closest point projections of one another on those 2 adjacent curves, and I could measure their relative distance or separation, which would be effectively measuring that value g, the kind of like the inclination of the hypersurface in this kind of hypersurface domain. So it turns out you can actually define this value of g, which I'll term the differential gap function, sort of like the conventional gap function in contact mechanics, as measuring kind of like the discrete difference in value of like the normal distance between 2 different points. But instead, using this definition of the delta-delta alpha derivative, g measures something more like the rate of change in the normal distance with respect to incremental changes in alpha. And it has, again, a geometric interpretation that can be defined in this limit sense by supposing that in general, you could define the delta-delta alpha derivative of some field f as really just the difference in value of that field f measured at these 2 adjacent closest point projection locations, and then divide by delta alpha, taken in the limit as delta alpha goes to 0. So it's sort of like a differential or incremental infinitesimal definition of a gap function, but which can also be generalized to measure something other than just, what's the separation of points, but potentially what's the difference, the differential difference between some field defined on 2 adjacent curves in this foliation. Okay, so now that we have these tools in our hands, we can do a lot of interesting things, but we still have to be a little bit explicit about how we define this intermediate hypersurface that we've come up with. The problem is we haven't been specific in defining what the geometry of this hypersurface looks like. It could be any, interesting looking wavy surface that connects these 2 curves. That's the only constraint that we have. It certainly has to, attach itself to these 2, surfaces, gamma 0 and gamma 1. But in between, we haven't been explicit in terms of defining what this hypersurface should look like. Now, to be totally consistent and to ensure that we have a unique description of this hypersurface, we have to subject it to maybe some kind of Euler-Lagrange equations or something like that, something that renders the geometry well-defined and uniquely defined. And one particular choice is this so-called zero normal curvature condition. There are certainly other, conditions that you could try to enforce, but this one is particularly nice in the sense that it insists that along any particular trajectory that one might follow, going from, let's say, gamma 0 to gamma 1, if I were to follow a trajectory that follows along the gradient flow of alpha, or in other words, if I were to follow a trajectory that traverses along, this manifold that is always going in a direction that's tangent to the local normal vector, then effectively I would be traversing a curve that, goes relatively smoothly from one surface to the other. Now, along such a curve, if we were to enforce this zero normal curvature condition, we would find that along such trajectories, that this differential gap function should be a constant value along each such trajectory, going from one surface to the other. And that can be obtained, again, by enforcing this condition that the delta alpha derivative of G is equal to 0 everywhere on this hyperdimensional manifold. Alternatively, or equivalently, we could pose that as being the solution to the minimization of this corresponding action functional involving the minimization of this integral over the foliated collection of hypersurfaces with G squared in the integrand. Now, the one thing that I'll point out about this whole notion of defining trajectories that go from one surface to the other is that it's a little dissatisfying to see that these trajectories are not straight lines in space. They're curved. So if I were to try to define a closest point projection or a mapping of points on one surface and the other surface, I wouldn't be able to find that that distance defined between them could be obtained by simply integrating G along one of these trajectories. That wouldn't necessarily give me a description of the shortest distance in a Euclidean sense between those 2 points. However, in the limit that these two surfaces come into contact with one another over some subset of their boundaries, I would find that along the interface where those two surfaces are in contact, I can justify that the points on those two surfaces will be coincident. And moreover, if contact is to be exactly enforced, then I insist that this differential gap function should be equal to 0 everywhere over that subset of this hyperdimensional surface. Now, if that's the case, taken in combination with our other condition of zero normal curvature, it's possible to show through a few manipulations, and I think Thomas probably has some of the details there. But effectively, you can show that the curvature of these trajectories that one would follow, going from gamma 0 to gamma 1, would reduce to simply straight lines or geodesic curves that are really equivalent in some way between our original description of our discrete gap function, measuring the normal projected difference of the positions of 2 points that are otherwise coincident in this case, that we would see that this discrete gap function is actually perfectly consistent with our definition of the differential gap function anywhere we have this condition that the two surfaces are perfectly in contact. So we don't actually have to deal with the issue of these trajectories being curved in that case. We're just working with effectively points that are perfectly coincident, and hence, the distance between them can be obtained just by integrating, G over this particular trajectory. Kind of nice. So we have perfect consistency with the original definition of our discrete gap function. Okay, the other thing that we need is, in order to enforce that the gap equals 0, we have to introduce some kind of constraint or some additional variable like a pressure field as one would do if you were to define some kind of Lagrange multiplier that enforces the constraint. And typically, that additional constraint taken together with the gap function would have to satisfy our Hertz-Signorini-Moreau conditions. However, we can't just define that contact pressure on one surface or the other of these two surfaces in contact. We actually have to extend its definition such that it exists everywhere within this hyperdimensional interface. So it's defined continuously over that whole intermediate domain, but we have to also supplement with another condition to ensure that that pressure field is well defined over that intermediate domain. We introduce a similar condition to the one that we enforced on the gap function, the zero normal curvature condition. So in other words, we say that the delta alpha derivative of the pressure field is equal to 0, which is equivalent to saying that along one of these trajectories where those two surfaces are in contact, that the pressure should be constant. Okay, so with all these different conditions put together, we can now formulate some hyperdimensional formulations of contact, which are really not so different in some respects to classical formulations of contact, which suppose that really there's only a few things you need to tweak or change. If you were to deal with a classical implementation of Mortar method or penalty method, the only things you'd need to change are substituting your definition for a discrete gap function with this so-called differential gap function defined in terms of the delta alpha derivative, and any integrals that you would carry out over a particular reference surface, let's say it's gamma 0 in this case, you would instead carry out those integrals over the full foliated hypersurface, so the full collection of gamma alphas parameterized by alpha between 0 and 1. That's it. That's really the only difference. And then you would pose the same kinds of additions to include this complementarity condition in your the formulation of a Lagrangian, from which you can then determine, well, what are the appropriate forces, and what's the resulting system of equations that I should solve, finite element context or what have you. But otherwise, very minor changes. Otherwise, it looks very similar. Okay. Now, if I were to solve this problem using, let's say, finite elements, it turns out finite elements provide a particularly convenient mechanism that can be used to evaluate some of these quantities of interest that we've defined previously. If I have a finite element discretization of this intermediate domain, it turns out that that finite element discretization gives me a piecewise local parameterization of the hypersurface expressed in terms of the parametric coordinates of the individual elements. And the nice thing about having such a parameterization is that through the Jacobian of this parametric mapping of a given element, discretizing this hypersurface, the Jacobian enables me to compute all these different quantities that I wanted. Things like the local surface normal, or rather the normal to a particular level set, if you like. It also gives me a means of computing directly this differential gap function, and also even the delta alpha derivative of these convective or parametric coordinates C, which can be used, to compute things like the delta alpha derivative of the shape functions of the element and so forth. And the interesting thing that I'll point out is that all of these quantities can be computed without having to actually invert this Jacobian. So even if the Jacobian itself, the partial derivative of the spatial coordinates x with respect to c, even if the determinant becomes 0 in the case when that element basically collapses, indicating that the two surfaces should be perfectly touching, that doesn't necessarily introduce a complication, because all these terms can be determined using instead the cofactor of J, the cofactor of this Jacobian. And that remains well defined regardless of whether the element becomes inverted or if it has 0 volume. So that's particularly nice. It means that it doesn't matter, even if the element inverts, indicating interpenetration, or if it's, perfectly collapsed, indicating, perfect contact, we're okay. Similarly, we can use these same pieces of machinery to pose integration over that foliated collection of surfaces. And it turns out that that foliated integral can be carried out through a simple change of variables. So we can integrate over our finite element domain using standard Gaussian quadrature rules, and we'll get, fully consistent integration in doing so. So a lot of really nice properties and advantages to using a finite element discretization, or, alternatively, having a parameterization of the surface would enable you to do similar things. It just so happens that a finite element discretization naturally induces such a parameterization. Okay, so let's see a few examples of this whole approach in action. Supposing I were to take all those things and implement it, here's a very simple example of a Hertzian type contact problem where I have basically a sphere depressing into this block. And I'm only using a single layer of these hyperdimensional interface elements, as you can see. And it doesn't give great results. It gives okay results, but I'll point out that if you take a look at this middle figure, you'll see that the contact pressure field being represented in those color plots in the interface, that it looks a little bit choppy. It doesn't look particularly smooth. And a lot of that has to do with the quality of the discretization that I'm using. I'm using a combination of quadrilateral elements and triangular elements. And, everybody knows, triangular elements are not particularly advantageous. They suffer from accuracy issues. And partly the issue is also to do with the fact that I'm just using a single layer of these hyperdimensional interface elements. And that is actually, partly a problem because it doesn't really give me a lot of flexibility to allow for that interface to conform to those two surfaces as they come into contact. So it's actually advantageous in certain cases to use more of these hyperdimensional interface elements through the thickness of that intermediate domain in order to actually get better accuracy. So rather than just using a single layer, as you might be constrained to using if you were to use like the classical contact domain method or some of those other methods, using more elements through the thickness, using H refinement, gives you better accuracy. Now, the alternative to using more elements would be to use, as you would do in an H refinement type of approach to get better accuracy, would be to instead increase the order of the elements, as in P refinement. So to illustrate that in a little bit more detail, consider the following example, where I have two cylinders embedded in one another, and they're allowed to slide past each other. Now, ideally, these surfaces are not pressurized, and there's no friction in between them, so they should perfectly slide past each other, and there shouldn't be any pressure that builds up in between them. However, if I were to use this approach, at a certain point, especially if I were to use lower order elements, at a certain point, you'd actually get a little bit of tangling to the point where those interface elements would kind of lead to some artificial compression between those two cylinders. So you wouldn't get perfect sliding going between them without any kind of interaction happening. However, if I were to discretize that same problem using higher order elements, in this case I'm using quadratic elements, both for representing the two cylinders as well as discretizing that intermediate hyperdimensional domain. And you can see at a certain point it does start to introduce, you can just barely see the change in color there. But there is a tiny bit of pressure that builds up once you've rotated these two cylinders close to 45 degrees relative to one another. But even so, it's surprising that you can get away with that without encountering so many problems. And really, the reason that you can do this has to do with the fact that as you increase the number of internal degrees of freedom to represent this hyperdimensional interface, as you would have in the case of these quadratic elements, that those extra internal degrees of freedom actually allow you to tolerate more relative sliding than you would have otherwise been able to, and still get away with reasonable accuracy. So that's kind of the secret ingredient here, is that if you increase the number of elements through the thickness or increase the order of the elements in this hyperdimensional discretization, that you actually can, manage to deal with moderate sliding. And obviously, the more elements you use, the more sliding you can tolerate. So all of this, in the previous example and this example, I'm demonstrating the use of a penalty-based enforcement of the contact constraints. In this example, I'm demonstrating the use of a mortar approach with a sliding-only enforcement. So I'm disallowing separation, but I'm allowing tangential sliding. And you can kind of see, how this would appear if I were to, allow those two beams to slide past each other along this intermediate interface as they kind of deform in a sort of non-uniform way. All right, so it does reasonable. I think I would say it's, again, it's using those quadratic elements, so it's able to tolerate relative sliding up to a point. All right, so all of that is kind of a nice demonstration of the results, but the thing that I want to spend the remainder of my time here on is actually discussing some of the challenges that I faced in coming up with variationally consistent forces for that kind of approach that I showed. And, the implementation of that actually took several iterations to figure out what is the correct expression to use for the resulting nodal forces in my, finite element discretization of these problems. And I pondered this for quite a while, and it took a while to settle on this approach, but I'm convinced now that this is the correct way to do this. So the problem is, if you're dealing with these delta alpha derivatives, as you would have in defining your gap function or your differential gap function, when you try to take variations of that expression, you might be tempted to say that such a variation can be expressed purely in terms of this delta alpha derivative. But it turns out that it's not sufficient to just consider that differential operator in isolation. You actually have to package it together with another differential operator, the surface gradient, which is really nothing more than the projected portion of the gradient of some function, let's say f, restricted to the tangent plane to a given level set. So, given the surface gradient and this delta alpha derivative, both of which can be expressed in terms of the partial derivatives of some function f taken with respect to both the spatial coordinates x and with respect to alpha, I can come up with some combined differential operator, which I'll refer to henceforth as the hypersurface gradient operator, which is really nothing more than the composition of the surface gradient operator with this delta alpha derivative operator. It is effectively a d plus 1 dimensional operator, which can be used to define a few other quantities, as I'll show momentarily. But the thing I'll point out here on this slide is that you'll notice the delta alpha derivative of a field f actually, it is really, it bears some similarities to a total derivative or a material derivative in the sense that it involves not just a partial derivative of some field f with respect to alpha, but some additional term that involves the partial derivative of f with respect to x, dotted with the delta alpha derivative of x. So in that sense, it is kind of like a total derivative, but it's sort of its own distinct thing. Nonetheless, I wanted to point that out just to emphasize that the delta alpha derivative is not the partial derivative with respect to alpha. It's a distinct quantity. All right. So having this new differential operator in hand, suppose, just taking a slight detour, suppose that we're not just dealing with a particular configuration of this intermediate hypersurface. Suppose that that hypersurface could undergo a time-varying sequence of deformations, measured relative to some particular undeformed configuration whose coordinates, hyperdimensional coordinates, can be denoted with all subscript zeros. And relative to this undeformed configuration, we can then measure relative deformations of this hypersurface in some new deformed configuration, which might vary as a function of time. So, given that we have some, let's say, a mapping between those two configurations, undeformed and deformed, we can then define a conventional deformation gradient, if you like. But because we're dealing with this hypersurface in this hyperdimensional space, we actually have to come up with a corresponding hypersurface deformation gradient. And it turns out that the appropriate way to define such a hypersurface deformation gradient is using this so-called hypersurface gradient operator. In particular, the hypersurface gradient operator measured relative to the initial configuration of the hypersurface. And in doing so, I can actually produce this hypersurface deformation gradient, which has a nice and convenient block-structured format, involving a term that basically characterizes just the in-plane or membrane deformations of a given level surface, as well as another term, which I'll call the differential displacement vector. It is effectively a measurement of the relative separation or a change in separation between two adjacent level curves, as well as its tangential component characterizing the relative slip between those two different surfaces. So in some sense, that gives you a description of not just what's the change in normal distance between two surfaces, but the slip, which can be used in the case of formulating things like frictional contact models and so forth. Using this hypersurface deformation gradient, I can also define a corresponding hypersurface velocity gradient, similarly defined using this hypersurface gradient operator and using similar terms like having a surface velocity gradient, again measuring the rate of kind of deformation in the plane of a particular level surface, and the differential velocity vector giving me sort of the rate at which those two surfaces are separating or slipping past each other in terms of the normal component and tangential components of that vector. Okay. All right, so the fun thing here, if you have a finite element discretization of a particular problem, you'll get a Jacobian for that particular isoparametric mapping. But that Jacobian won't necessarily have a complete number of columns. It will be a little bit lopsided. You'll have more rows in your Jacobian involving, the spatial coordinates x and this hyperdimensional coordinate alpha. More rows, corresponding to those hyperdimensional coordinates. Then you have, coordinates associated with the parametric domain of the element, or represented in terms of the parametric coordinates c. So it turns out that obviously that means you can't invert the Jacobian anymore because it's not a square matrix. And even if it was a square matrix, it might not necessarily be invertible. However, if you were to make a slight modification to that Jacobian by adding an additional column that comprises just the normal vector and then 0 in the component where you would have a hyperdimensional kind of entry, then in doing so, you form a square matrix for this hyperdimensional Jacobian, as I'll call it, which is in fact invertible, and which actually facilitates in a very nice way the computation of these other deformation quantities that I've just defined, the hypersurface deformation gradient and the hypersurface velocity gradient. And so all those things taken together actually make using a finite element discretization or some kind of parameterized representation for the hypersurface a very appealing strategy. Obviously, you can use this also to compute the hypersurface gradient of the shape functions, and that has various utilities, as we'll see momentarily. But the other cool thing that you can do, if you have such a description of a hypersurface deformation gradient, using that hypersurface deformation gradient, we can define effectively these hypersurface deformation measures in an analog to conventional continuum measures of deformation, like the Green-Lagrange strain. In other words, suppose I had some hypersurface deformation gradient, and I defined this hypersurface Green-Lagrangian strain, which too has this block-structured decomposition to it in terms of, let's say, a membrane or planar version or component of that deformation represented through E, capital E with a bar, as well as what I'll call the corotational differential displacement vector, which is really nothing more than the differential displacement vector, but involving F bar transpose, ensuring that you effectively have a description of normal separation and slip, which is invariant to rigid rotations. Now, the nice thing about formulating a contact constitutive model. And what I mean by a contact constitutive model is either a penalty-based formulation of contact to enforce the zero interpenetration constraint, or potentially even a formulation of frictional contact expressed in terms of this hypersurface deformation measure. If you form a potential expressed in terms of this hypersurface deformation measure, then you ensure that the resulting forces that you derive from that potential will be frame invariant. That's one nice thing. But also you ensure that you have other nice properties, as we'll kind of get into. So given this hypersurface deformation measure like the Green-Lagrange strain, and given a frame invariant potential expressed in terms of that deformation measure, you can come up with a corresponding hypersurface stress tensor, much like a Kirchhoff stress or whatever you like. Second Piola-Kirchhoff stress, Cauchy stress. There are various equivalents, but they're all symmetric in this particular case, which has certain nice and beneficial properties in the formulation of the residuals. So, given these definitions, I can then, in a generic way, suppose that for a particular expression of this, I guess you could call it the hypersurface, potential function that expresses that contact constitutive model through the definition of this kind of like potential function psi, I can come up with a corresponding contact stress power term expressed in terms of that hypersurface stress tensor, taken with an inner product with the hypersurface velocity gradient. And that gives me a variationally consistent description of how these corresponding nodal forces should arise in the context of my contact virtual work. So interestingly, if you plug all that in and you work through what the particular expressions are for that contact hypersurface stress tensor should be, then you'll find that the resulting expressions you get include an additional term as highlighted at the bottom here. So including that extra term is essential for ensuring that the resulting nodal forces you get are variationally consistent. You wouldn't get that if you didn't go through this whole process and insisted that you come up with this fully coupled hypersurface gradient operator that composes both the delta alpha derivative with the surface gradient, basically. So you need both of those things combined together to ensure that when you take these derivatives, that you get the right stuff. So I won't go into the details. I'll leave it more for the forthcoming publication to dive into a lot of the how you actually formulate these things and what the specific form for these forces looks like when you look at things like simple frictionless contact constraints. But I will point out that there's a lot of ongoing work planned and underway to expand on this framework and to incorporate things like frictional sliding. So there's a lot of stuff to look forward to. Now, I will point out that even though I've said there's a lot of advantages to using a finite element discretization in combination with this whole theoretical framework, that nonetheless, if you are restricted to require a conformal discretization of this hyperdimensional interface, then that can really, impose quite a lot of burdens on how you actually go about enforcing the contact. Because obviously there's only so much deformation and relative sliding that you can tolerate until you have to remesh this intermediate domain. And if you do that, then you can mess stuff up in the process of trying to remap solution variables from one discretization of the intermediate domain to another. So it would be nice if there was an alternative way to discretize that intermediate domain, or to ideally not even have to discretize it at all, but still rely upon the same underlying machinations of this hyperdimensional formalism to be able to formulate contact in a more flexible way that gives you maybe smoothly varying descriptions of a gap function or other interesting benefits. So potentially using things like mesh-free methods or boundary element methods might enable precisely those innovations, but it remains to be seen, and there's a lot of work to do on that front. The other thing, and the final thing that I'll point out here to answer the opening question, how does contact mechanics relate to the theory of general relativity and the underlying mathematics that underpin that theory? Well, it turns out that, it took a little bit of digging, but it turns out that there's something called the ADM formalism, named after Arnold, Desser, and Misner, which is a particular description of Einstein's theory of general relativity that is expressed by considering a foliation of space-time into a collection of space-like curves on which you can formulate a Hamiltonian description of all of the quantities of interest in general relativity. But in describing such a foliation, you can also induce the description of something called a lapse function and a shift vector. And it turns out that the direct analogs in the case of this whole hyperdimensional discretization of this contacting interface idea, that in fact, that actually has a direct analog to the descriptions of our gap function, the differential gap function, and something like a tangential slip vector. So surprisingly, a lot of the mathematics is similar, and maybe unsurprisingly, because ultimately it all just comes down to differential geometry in the end. We're not dealing with Minkowski spaces and anything fancy like that. We're still dealing with primarily Riemannian geometry, or at least so far. We'll see. Maybe we'll extend it to Lorentz manifolds and stuff, and that might be an interesting innovation. But for now, supposing that we do this, there's a lot of cool things that you can do and cool connections with some fascinating theory from these other approaches. So it'll be interesting to see how much of that theory carries over and applies in the context of contact mechanics, but that's another open question. Otherwise, I appreciate your time and attention. If you have questions or want to express an interest, definitely reach out to me. I'm more than happy to chat with you. Otherwise, thanks again, and I'll see you next time.